Constraints. The first talk will be given by Marco Franceschetti, and this is joint work with Johan Eden. Title of the talk is Negotiating Temporal Commitments in Cross-Organization Business Process. Marco, you have 15 minutes, and after 12 minutes, I will give you a sign.
Okay, thank you very much. So I start.
Yes.
Welcome and thank you very much for the introduction. So my name is Marco Franceschetti. Together with my supervisor, Professor Johan Heder, we have been working on cross-organizational business processes for quite a while now. And with this work in particular, we addressed the problem of the negotiation of temporal commitments in such type of processes. Now, in a nutshell, a cross-organizational business process is a phenomenon which emerges from an ensemble of local processes which are executed at several companies or organizations in order to perform a final common goal, such as the purchase of some goods from some online store. And in this case, we have companies such as an online store, credit card companies, banks, warehouses, and whatnot. Now, in this setting, all these participating parties are executing their local processes, but actually what we see in the interaction is only process views and message exchanges, because the common way to realize such processes is aiming also at hiding the internal implementations of the local processes for business secrecy. So we have basically a number of interactions and message exchanges between these parties with no particular view in the internals. For a more concrete example here, we have a very simple procurement process which involves three parties. We have a distributor of medical equipment, a factory producing surgical masks, and a supplier of raw materials. We have interactions such as the request with an order from the distributor to a factory. The factory in turn may contact the supplier requiring the raw materials to be delivered. Maybe then the supplier is allowed to be in contact directly with the distributor to appraise the requirements. Then materials are delivered and the final product is shipped. And all these are simple interactions without any view on what is actually executed at each local party. If we take a look inside there, then here we have the local process simplified for the factory, where we see we have a number of tasks which are executed but are invisible to the others. And here we see some vertical arrows between the pools which represent the interactions, but inside we have tasks such as gathering material, preparing boxes, packaging, and so on, where we have also a number of elements such as durations for these tasks, which are here represented in square brackets to show intervals for durations, so some duration between a minimum and maximum. And also temporal constraints, such as the rightmost here, C3, which impose some restriction on the occurrence of events. So for C3, for instance, it is required that the delivery of the masks is completed within 2 days after the packaging has been finalized. More in detail about the temporal aspect of these local processes that we're seeing here. What we consider is, in particular, time points for events, such as the start and the end of tasks, durations, where we distinguish actually between non-contingent and contingent durations. The difference is basically in the fact whether the duration can actually be controlled by the executor, or it can be merely observed to fall within some specified interval, but with no control over it. Then we have temporal parameters, which basically encode timestamps for events, and they can be transmitted between local processes. So they can be either inputs or outputs to actually, as we have shown with previous work, enforce temporal constraints requiring certain events at other local processes to occur within certain bounds without actually having to access the internal of the process. And in fact, for temporal constraints, as listed here, we distinguish between upper bound and lower bound constraints, which are basically imposing some maximum or minimum time lapse that needs to be to hold between two given events. So concerning cross-organizational constraints, they are basically expressing commitments for the parties to execute their processes. And these are constraints on the admissible time points for the communication of events. So when should I send something, or when should my partner expect to receive something from me? Or also values for temporal parameters which can be transmitted between the parties. The goal is actually to reach in the design phase of the process an agreement between all parties on a set of constraints on these parameters such that they lead to only temporally correct executions of the process. And what do we mean by temporally correct executions here in the case of a cross-organizational process? Well, we mean that the whole cross-organizational process is correct when all the local executions with the temporal parameters are temporally correct. And for temporal correctness here, we need to consider that we have locally two sources of uncertainty we need to cope with. One is these contingent durations, so durations which can be observed but not controlled by the executor. The other is the uncertainty which comes from the input parameters which are received at a local process, because these are ascended value by someone else, and there is no way to change it afterwards. Because of these uncertainties, here we advocate for the concept of dynamic controllability as the most suitable notion for temporal correctness of a local process, and thus for the whole collaboration. Now, we need to make an observation here. We have these partners which make commitments, constraints on the parameters they exchange. And we observe that actually what is an input parameter for one local process is always an output for some other local process in the collaboration, which means that a constraint on a parameter is a guarantee that a parameter will take only certain values for the receiving side, but it is an obligation for the sending side to assign to that parameter only the specific values which fulfill the constraint. And one thing we need to observe here is a conflict. So for a receiver of a parameter, if this parameter has a wide range of values which are allowed by these commitments, it means that for the receiver, there is a higher degree of uncertainty because there is a much wider range of values this parameter will have to take, and thus the receiver will need to cope potentially with a much larger set of values. So they may prefer to have a more specific, more small range of values. On the other hand, though, for the sender, a narrow range means that it may be more difficult to actually satisfy the temporal constraints at the local process. To give a very small example for that, I experienced this a couple of days ago. This is not an actual screenshot, but so there is an online store, I guess you know which one I'm talking about, which guarantees for its prime customers delivery also on Sundays now. And it happened this last Sunday that I got notified that I would be receiving a package on that day by 9 p.m. This for me was very bad because I actually had to cancel all my plans for the day, waiting there at home for my package to arrive because I didn't want to have it left at the door. Of course, I would have preferred a smaller range indicated for the delivery, but for the courier delivering it, it would have been much more difficult to give such a specific smaller range for the delivery. So we want to support process designers with the following computation. We want to compute which are the widest ranges for the input parameters which can be accepted by a receiver. And as well, which are the narrowest ranges which can be accepted for a sender of an output parameter, such that these values are compatible with the dynamic controllability of the collaboration. In addition to that, we found out in our research that actually we have interdependencies between parameters potentially. And also these are constraints between pairs of parameters, which we may need to enforce and communicate to the respective partners who need to assign values accordingly to these parameters. So our approach is the following. We decided to rely on temporal constraint networks, and we start by mapping each local process, the collaboration with the temporal parameters, into an equivalent STNU, simple temporal network with uncertainty. We apply some constraint propagation technique at each local STNU with parameters to compute the actual restrictions on the parameters which need to hold for that local process. And then we have basically a loop which we can iterate over, in which these restrictions are sent and received between the partners. And when some restriction is received, it is introduced newly in the local STNU. And then we go on recomputing parameter restrictions, whether in the case these are needed for newly received restrictions that are requested by others. We do so until we reach a fixed point. That means no new constraints can be derived. And then at that point, we lift these computer restrictions again at process level, and these are restrictions which need to be enforced by all the involved partners in the process. So we start by mapping processes into STNUs. We have defined in some previous paper also mapping rules, which allow us to map a local process into an STNU. So each temporal element of the process is basically mapped into a STNU element. The good thing about using STNUs is that we can actually also employ some techniques for checking the dynamic controllability of the STNU in order to check the dynamic controllability of the local process with parameters. Then for the propagation constraints, actually we needed to develop a new set of rules compared to the ones that we can find already in the literature, because we needed to compute restrictions for temporal parameters which are actually independent from any contingencies which are present in the process. We called these three rules P rules, because they are somehow inspired by the rule system which was developed by Massimo Cairo and Romulizzi. And these allow us to derive actually non-contingent STNU edges for the temporal parameters, which are independent of any contingent duration. When we do so, then we apply these rules until network listens. Then we look at the derived edges between the zero time point of the STNU and these parameters, and these basically tell us which are the ranges in which these parameters need to fall when we need to assign them a value. And also we look at the edges which are derived between pairs of parameters, because these represent additional constraints which we need to fulfill in order to have a dynamically controllable process. I guess we have 2 minutes 15, right? Okay, thank you. Once we have computed these restrictions, we have all our communicating STNUs which send the computed restrictions to the others, receive the computed restrictions by the others. These are included in the local STNU, and we again recompute, if necessary, the maybe tighter restrictions which we need to enforce into our parameters in order to cope with the restrictions which we know the others are requesting from us. In the end, what happens? Either we get a negative cycle in some of the local STNUs, which means there is no existing set of constraints which can guarantee the dynamic controllability for the process, or we reach a fixed point, so no new edges and also no negative cycles. And this means we have computed the set of constraints which we need to enforce into our process for dynamic controllability. Actually, for the communication here, it's a distributed process, so we have several variants for making sure that everybody knows when a fixed point is reached. Here we are proposing as an early work an approach which is based on the fact that every restriction is shared among all participants, but we also may have different approaches such as a central coordinator which acts as a mediator, global hierarchical processes, or even fully distributed procedures which are based on the distributed cycle detection. To conclude very quickly, In time-constrained cross-organizational processes, it is a necessity to negotiate temporal obligations and guarantees between the participants. We have shown with previous works actually that temporal parameters are an adequate means for expressing these obligations and guarantees while preserving the secrecy of all the local processes involved in the collaboration. Here we propose the distributed procedure for computing these restrictions in terms of ranges and interdependencies between parameters. For the future, we plan to investigate the variants for the implementation of the fixed point detection approach, and also to adopt more expressive temporal networks, such as STNUS as the underlying formalism for increased explicitness. So thank you for your attention. Sorry for taking 20 seconds longer. Now I'm glad to take any questions from your side.
Thanks, Marco. So, questions from the audience, if you can unmute yourselves and ask, or write in the chat.
Yeah, I have a question. Can you hear me?
Yes.
Okay, great talk. And besides using more expressive formalisms of temporal networks, have you thought about also exploring other kinds of controllability? For example, strong controllability. Weak is not really useful in this context, but maybe strong controllability could be.
Yes, sure. There is actually a number of notions of controllability from the strong to weak dynamic. Actually, a strong would also hold very nice guarantees, and it is an interesting one which can be explored. Okay, I also see you now. The thing is, it allows less flexibility for the execution of local processes, but then it is a matter of what are the requirements and whether this is acceptable for the participating parties. Yeah. There is also some other notion for controllability, which we will hear tomorrow in the keynote, so no spoilers on that.
Yeah, maybe because I was thinking about the example you introduced before about the delivery. Maybe, yes, strong is of course more restrictive, but maybe it could be useful because could lead to say that your package will be delivered exactly at that hour.
Yes, definitely. It can provide better guarantees, but my take on this is that it is dependent on the application area. So in certain cases, there is some dynamic aspect which cannot be given up on. So, but for sure, strong controllability is definitely another interesting one, which is worth investigating on.
Okay, thanks.
More questions from the audience? So Marco, I was just wondering, are you in a collaboration with any organization, and just to get some idea of how large these networks can get? And
okay, so currently this is only academic project. We are not in contact with any particular organization where this have a direct application. Concerning the applicability and the size of the temporal networks, so it depends on the type of the temporal network. We have different complexity. So for STNUS, we have the advantage that the complexity of the algorithm is polynomial. If we want to go to something more expressive, such as the STNUS, then the complexity increases. Right now, to be honest, I don't remember the exact complexity for STNUS, constraint propagation. On this, I need to check the work of Roberto Posenato, for instance. But we have done a few experiments, actually, also for this type of temporal networks with reasonably sized processes. While theory would tell us, forget about it, the complexity is much worse than polynomial. Actually, the times we are experimenting are still somehow reasonable, especially because we are talking about the design time of business processes. So it's all operations which are done before everything is put into operation. So we can even afford spending hours or a few days for computing constraint propagations in order to get an answer.
Mm-hmm.
So we have actually a more application-oriented point of view, I guess,